Welcome to EPG Pathshala. Today we are going to learn on Groundwater Hydrology Part 4 course, and we are specifically dealing with Module 17 of the course that titles Coupled Flow and Transport Problems. Let me briefly introduce you to the problem or the coupled flow and transport module. By coupled flow and transport problem, we mix or combine both flow and transport. In the flow part, we mostly deal with the quantity issue of the problem, of the water problem, whereas in transport problem, we basically talk about quality issues. In this module, we are going to couple flow and transport, but we are mostly dealing with the flow problems and only briefly introducing you to the transport problems. Towards the end of the module, we are going to combine them and solve an example problem. So let us start with learning objectives of the module. The first objective would be to understand groundwater flow and flow model. Then we will focus our work on factors and processes that affects mass transport. Subsequently, we will move to derivation of transport models, and finally we will solve transport problems. Let us begin with the aquifer, the model aquifer, so as to say. And the model aquifer is actually called a representative control volume. Why this is required? Because aquifers are mostly very extensive, but their property changes in a very small scale, and this can be seen in the figure on the right. As you can see, their property is changing in each layer, and they are changing in a very small scale. When I impose a small unit into it, you can already see the changes in the properties. So a model aquifer has to be small, but it should not be very small or smaller than the pore size. Whereas the basic principle, groundwater hydrology principle, that is Darcy law, has to be valid in this RCV. Now that we have our our model aquifer, let us begin with the derivation of flow model. A flow model deals with flow of water without inclusion of any mass. That is to say that we are only talking about amount of water and not anything dissolved in water or suspended in water. So before I go on derivation, let me explain you how the flow occurs in our model aquifer or the RCV. As you can see in the figure, there is a water flowing from the left end, that is VFY, and towards the right end, right face of the RCV, which equals to the amount of water that has been flowing from the left end and the accumulated water that is coming out, which equals to VFY plus the added water, that is dVFY divided by dy, and the space that has covered delta y. This is also the case in the x direction and also in the z direction. So this is our basically a flow model. Now to derive a flow model, we require two fundamental groundwater principles or physical principles. The first one is the Darcy law, and the second one is conservation of mass in RCV or in our model aquifer. Now, what is Darcy law? A Darcy law is a very simple water transport statement, which states that a specific discharge, that is Vf, equals to K, that is hydraulic conductivity, times the ratio of head difference over the distance x, change in distance x. The ratio of dH by dx is also called hydraulic head gradient, and this hydraulic head gradient actually defines how and the direction and how rapidly the flow will be taking place. The negative sign in the front of equation states that the flow is from higher head towards the lower head. That was on Darcy law or Darcy principle that is required for derivation of flow model. Next, we decide conservation of flow in RCV. The water flow in and out of RCV is conserved, and that is the statement of conservation of mass. Mathematically, the conservation model principle says that the ratio of change of water volume in the RCB over the time delta T equals the amount of water flowing in through the phase in particular direction, that is Q in, minus the amount of water that is flowing out from the opposite phase. And this we have to do it in all the phases of the three-dimensional aquifer model that we have. Now, in order to derive flow model, we have to find the expression for each of these quantities that are available in the flow Darcy model and conservation of mass equation. Let's start with the finding the value for Q in. Q in is basically a conservation of mass, that is A times V, that is velocity times area, and this area in this case is the phase area perpendicular to the flow direction. Now, in the first case, along the x direction, the area would be along y direction and z direction. So that's what we have, Vfx times delta y and delta z. Similarly, it is for in y direction, and similarly also in the z direction. Likewise, we can also obtain Q out. Q out, if you see the RCB model, is basically the quantity that is coming out, and if you see along y direction, it is Q V Fy plus delta Fy by delta y times delta y. So what we do in the derivation is that we sum up all the amount of water that is exiting from each side of the cube and sum them together. Now we can find Q in minus Q out, or Q in minus Q out, and we can get the expression that you can see in the screen. So now we have our expression for Q in minus Q out. Next, we have to find the expression for change of volume of water. This is a little bit tricky because it requires another groundwater property that is called specific storage to define it. If you go through the text of this slide, you will see that this has been defined as, the change in volume of water has been defined as specific storage times change in hydraulic head in the space that has been covered times the volume of the model aquifer, that is delta x, delta y and delta z. Now we have, from the conservation of mass model, we have Vw, we have Q in, Q out. Now what we do is we put them together, and when we do that, we get an expression as you can see in the screen over here, that is SS delta H by delta T equals negative partial V Fx by partial D x, and it continues. Now finally what we could do is that we could put an expression for Vfx, or we could put an expression for specific discharge from our Darcy law, which is using Vfx equals to minus k dH by dx. In the model equation, this becomes the differential becomes partial differential as we are dealing with the 3D problems. Okay, now what we have is that we have derived a very fundamental flow model. There are different forms of flow model. The most visible one is a Laplace equation, which is for constant conductivity and deals with the steady state conditions. When we say steady state, we mean that the time derivative is 0. So that results to the equation that you can see in the screen, that is d square, a partial square h, partial s square, and all the sum of all the hydraulic head equals to 0. It is to be noted that the flow equation is a second order partial differential equation and is linear on hydraulic head. The other form of flow model that you can see we normally observe is a Poisson equation. Poisson equation again deals with the steady state condition, but it has it includes a source. By source we mean that there is an additional flow of water coming through the system, and it takes the form as you can see in the screen. Now that we have a flow model, different forms of flow model, but it is important to note that models or the partial models are not complete without the statements of initial conditions and the boundary conditions, and this has to be also defined in our flow model. When we say initial condition, we basically are dealing with a transient problem, and in transient problem the head has to be specified at time equals to 0. Okay, when we deal with constant steady state problems, boundary conditions has to be defined, and in groundwater flow problems there are 3 types of boundary conditions. The first boundary condition, also called the first kind, is the one in which heads are specified at x, different x, y and z. The second boundary condition, or also called the second kind, in this type boundary condition, head gradient is specified, that is in dh by dx or dh by dy is specified. Now this is a very special boundary condition, because this boundary condition is also used to define the no flow boundary condition, and this can be done specifically by making dh by dx or the gradient equal to 0. If there is no gradient, there is no flow, and this specifies the no flow condition, or a water not flowing or passing the boundary. Then there is a third type of boundary condition, also called the third kind. This boundary condition combines the first kind of boundary condition and the second type boundary condition. Mostly that our problems, general problems, we deal with second type boundary condition and first kind boundary condition and the second type boundary condition, and in a very special cases only we deal with the third kind of boundary conditions. Okay, now that we have completed our flow model, we will swiftly move to the transport problem. As I already said in the introduction, that in the transport problem we are dealing with the mass that is flowing along with the water. So before we start developing the model, we will start with the processes that affect the mass transport, or the processes that has to be put into the transport model. And there are 3 specific processes that has to be put or considered. The first one is called advection. Advection is the transport of mass with the movement of moving medium. That is, water is thoroughly being moved along the flow. Okay, this can be mathematically defined as mass flow rate, or the advective mass flow rate, JADV equals QC, where Q is the discharge and equals to AV, or area times the velocity. Of course, we have to add effective porosity, which means which deals with the connected pores, and C is the concentration, mass concentration in the model aquifer. Okay, next process that is important in the mass transport is mechanical dispersion. Mechanical dispersion is also a physical process, but it also involves a chemical concentration change, gradient. So it is basically a physiochemical process, and this is mathematically described by the mass flow, dispersive mass flow equals to a constant called d mech, which has a unit of which has a dimension of L square by T, and times the area and the concentration gradient delta C by delta L. Of course, this has to again be connected with the connected pores, and that is quantified by effective porosity, that is Ne. The third process that affects mass transport is diffusion. Diffusion is entirely a chemical process. It is a concentration gradient related spread of mass, and it is mathematically defined by diff J diff, or a mass flow, diffusive mass flow, equals a diffusive constant times area times concentration gradient. In practice, we combine diffusion and dispersion processes, and we generally come up with the third mass flow rate, that is called hydrodynamics mass flow rate, or that is being abbreviated over here as JDISH, H. Now that we know the process of that affects the mass flow and mass transport, let us try to derive a transport model. The transport model is derived in analogous to flow model. RCV is again used, and we have same two analogous main principle used in its derivation. Before I go on the principles, let me just show you the difference between the flow and the mass problem in our transport model, in our model aquifer. When we, as in the flow, we dealt with the discharge in. Here we are dealing with the mass flow in, and then we are collecting the mass flow that is going out, just as we did in the flow. This is also done in all the three directions, and instead of quantity of water, we are dealing with amount of substance over here. So let's start now with the derivation. The conservative equation for the mass transport is that the change in mass over the time t in the model aquifer equals the mass flow rate in the inlet minus the mass flow rate at the outlet. Now, to derive this mass transport model, we'll have to come up with the expression for each of these terms that is in the conservation equation, as we also did in the flow model derivation. Let's start with expression for delta M, or change in mass in the aquifer, model aquifer. This is simply volume, the volume of the model aquifer, or the volume of the RCV, times the change in concentration. Of course, it has to be multiplied by the effective porosity, because that is where the water is flowing. So this can be simplified as Ne delta X delta Y M. Here M is the thickness of the aquifer. We have used instead of delta Z for simplicity, and delta C. Now we have delta M. Next we will find the expression for mass flux, which is mass flow rate divided by the facing area. That is, in the x direction, it is simply Zx M, which is the thickness of the aquifer, times the width of the aquifer, delta Y. Also, we can do it also in the other spatial direction. That is, we can find the inlet Jy times the facing area, that is M times delta X. In this transport model, we are only dealing with we only considering two spatial directions, because for the simplicity. Now we have J in. Let us try to find J out. J out is again small z, that is a mass flux in the outward phase, is again mass flow rate coming out of the aquifer, or the model aquifer, divided by the facing area, and this can be obtained as you can see in the screen, or also you can see in the figure that we showed you in a couple of slides back. Now, as the expression requires that we need to find the difference between J in and J out, we do it over here, and we see that we get the expression that is in your screen. Please note that Jx has been defined as the advective mass flux plus dispersive mass flux plus diffusive mass flux, and we have combined dispersive mass flux and diffusive mass flux. So Jx, or the in x direction, or the mass flux in x direction, is sum of advective mass flux plus hydrodynamic mass flux. When we insert all the values of J in, J out and delta M, we obtain our fundamental transport model that you can see in the screen. If you want to see a more detailed derivation, a detailed stepwise derivation with explanation, you should see the text that comes up with this presentation. The model that you see in the screen is also called advective dispersion model or AD model. Please note that we are not dealing with chemicals or a mass going through chemical transformation. We're just talking here about mass that is being transported and not being chemically affected. This is sometimes also called a conservative mass model or conservative transport model. Now that we have a model, just as we had in a flow problem, we also have to define the conditions, the initial conditions and the boundary conditions to complete the transport model. As we said, in a flow model, IC or an initial condition deals with a non-steady problem or the transient problem, and in this case, concentration instead of head that was in the flow problem at this time equals to 0, or at the start of the simulation or start period of the analysis has to be specified. When we are dealing with the steady state problem, instead of initial condition, we need to define boundary conditions. So for the boundary condition, analogous to the flow model, we have 3 boundary conditions. They are the first boundary condition of first type, or also called the first kind. In this boundary condition, we have to specify concentrations at different space. In the second type of boundary condition, also called the second kind, we define the concentration gradient. If you remember, in the flow we defined hydraulic head gradient. Like in the flow model, in the transport model, we can specify the dc by dx, or the gradient is also used or can be used to specify no flow, no mass transport condition. In that case, we equate dc by dx, or the concentration gradient, equals to 0. Lastly, we have a BC, or a boundary condition of third kind, which combines a boundary condition of first kind and a boundary condition of second kind. Of course, the boundary condition of third kind is definitely a more complex one and is mostly used in special cases. Normally, we use boundary condition type 2 and boundary condition type 1, or first kind, and boundary condition of second kind. Now we have completely derived our flow model and we have derived our transport model. It is time that we try to solve these problems. It is to be noted that the transport problem also includes the flow. The flow mechanism is also included in transport problem. So when these kind of problems are solved, these are all mostly solved as a coupled problem, in which first the flow problem is solved and the head in the aquifer is obtained. Once the heads are obtained, the velocity fields are obtained, and then these velocity fields are used in the transport problems. Specifically, the coupled problem, and I would rather focus on transport problem over here, they are solved by 2 different approaches. They are analytical approach. In this analytical approach, exact solution, but mostly for simple problems and simple initial conditions and boundary conditions are obtained. Analytical approach can be a very simple one-line equation, but they are mostly not very practically useful, because the practical condition, as we saw in RCB, when we defined RCB, is very complex. Now, to overcome the problems of analytical approach, we solve the problem numerically, or sometimes we call it a numerical approach. In numerical approach, we get an approximate solution of the problems, and computers are used to solve this problem. This approach can have a very complex boundary condition, combination of different types of boundary conditions, different types of geometry, and they can be solved. However, it requires powerful computers. Different approaches are also available to solve problem numerically. Finite difference method, FDM, which is very widely used in groundwater flow problem, is more common in flow and transport problem. Finite element method is other method that are also used, and there are many more approaches, numerical approaches, that are being used that to solve the flow and transfer problem. In between analytical approach and numerical approach, we also have the third approach. Sometimes we call it a semi-analytical approach, which combines some form of numerical approach, and these are also very useful because this becomes an easier alternative to numerical approach. But in this module, we are not going to deal too much about or we're not going to deal anything about numerical approach because they are of more higher level courses. I will show you next few I'll show you at least one solution of the transfer problem. Let us begin with a transfer problem, a very simple transfer problem, which is dc by dt equals to dispersion dc square by dx square minus p dc by dx, and we have a initial condition that at any x at t equals to 0 the concentration is C0, and we have a boundary condition that C, the concentration at any time at the start of the domain or at x equals to 0 is equals to C in, and C at x equals to infinite at very far away from the inlet at any time equals to 0. So here we are considering the aquifer to be infinitely long, which makes sense because we know that aquifers can be very extensive. Now, the solution of this problem is given by Ogata and Banks, 1961, and the solution is put into your screen. Basically, as I said, that the analytical solution is a simple equation, and that is what you are seeing in the screen. The only thing new thing that may be for you is the ERFC, which is called the complementary error function. This is an integral function, the value of which can be found tabulated. Now, how do we interpret this solution? How do we interpret the problem? This can be mostly done by simulating different scenarios, and that is what is seen in the next slide. The solution can be interpreted by plotting the results obtained by varying. For example, we vary many length of the aquifer, we vary the inlet, we vary the velocity field, or we vary different inlet concentration. And what you can see in the screen already is that if I am varying this in different quantities, you can see that using Ogata and Banks solution, the steady state condition is reached at t equals to 5 hours. You can have these simulations and the mathematical codes, the codes that is used to develop this plot, and several others in my website http://github.com /Pravas UGC Transport. There are many more details of these, many more examples of a transfer problems are presented. I specifically encourage you to go through those problems and try to simulate these problems and check the results. Please note that the solution, the flow and transfer problem solution may look vague if you don't visualize it. It is more clearly observable when you put it into a plot, and this is the reason why I have developed this website. Towards the end, let us summarize the things that we have learned today in this module. I'll put upon you 4 specific statements. The first one, we have learned to systematically tackle the coupled flow and transport problem. Second point, we have learned about the different processes that affect flow and transport problems. The third point, we have learned about how to derive a problem or a governing equation for the flow and transfer problem and formulate it together with the initial and boundary conditions. Finally, we have learned how to solve simple flow and transfer problem using analytical approach and visualizing them. I am sure that you have learned a lot already to get started with the more complex flow and transport problems. Thank you.